Paper 2, May 2019, AS. Question 1. The structures of 3 organic compounds A, B and C are shown below. So remember, these are skeletal formulas. So at every point here, then there's a carbon with some hydrogens as well. So I've got a carbon here with a double bond O. Going to another carbon here, I've got a CH3 here. So this is a ketone. Here I've got a carbon with a double bond O and an OH, I've got a carboxylic acid. And here I've got a ring and I've got a carbon with a double bond O and an H. I've got an aldehyde here. So I've got a ketone, a carboxylic acid and an aldehyde. Now I've got to distinguish between them. So how do I distinguish between A and B, a ketone and a carboxylic acid? The easiest way is to test for a carboxylic acid by adding something like sodium carbonate. Observation with a ketone, no change, no reaction. Observation with B is that I'm going to get bubbles. Compounds A and C, so between the ketone and the aldehyde, I could add something like warm Tollens reagent or Fehling solution. I'd get no reaction, I'd see no change with the ketone, but with the aldehyde I'd see a silver mirror if I'd chosen to use warm Tollens, or I'd see a brick red solid, a brick red precipitate if I'd decided to use Fehling solution. Outline the mechanism. So I've got bromoethane here and I've got potassium cyanide making propane nitrile and potassium bromide. But remember, in the mechanism, potassium cyanide dissolves in the water. So we use something like methanol and water as a solvent here, and it will make Cn- with a lone pair of electrons, and it's that you've got to use. The K is a spectator ion. Don't include the K in the mechanism at all. I've got a Cn- ion, I've got a lone pair of electrons on the carbon of the Cn. That will attack the delta plus on the C, on the polar bond between the C and the Br. Remember, the Br is electronegative, so it gets a small minus charge, and the C gets a small plus charge, delta plus and delta minus, so I've got a polar bond here, and the lone pair of electrons attacks or bonds to the carbon of the CBr. The electrons then go from the CBr bond onto the Br. So the Cn then bonds to the C, so I end up with CH3CH2Cn, and the Br gets a minus charge because it's had electrons moved onto it. The Cn part doesn't have a charge because it's had electrons move away from it. Give the name of this compound here is propane. Remember, there's a carbon there, 1, 2, 3, so it's propane, single bonds, and an N is a nitrile, propane nitrile. Calculate the percentage atom economy for the formation of D in this reaction. So what I do is I look at the desired product, which is this that I'm making, and divide by the MRs of all of the products. So percentage atom economy is the MR of the desired products divided by the MR of all the products. So the desired product here, I've got 3 carbons, each 12 is 36, hydrogens, 5 ones is 5, and 14 for the nitrogen, and then all of them is that again, plus the sorry, I'm doing it from here, from the KBr. So the KBr, the K is 39 and the Br is 80. So in this reaction, the mass, the MR of the propane nitrile is 36 add 5 add 14, and the mass of everything on the right hand side is 36 plus 5 plus 14 plus the K, which is 39, plus the Br, which is 80. And I work that out and it'll come out as 55 divided by 174 multiplied by 100%, 31.6. I've put it to 3 significant figures. It says the appropriate number of significant figures. I've decided to use 3 significant figures because most of my MRs will be or could be to 3 significant figures.